Alrighty, so this is lesson 7-2, and we are going to be proving lines are parallel. That's the name of the lesson, proving lines are parallel. If you remember from lesson 7-1, we kind of introduced these parallel lines and the angle relationships that they form. So now we're going to be using these angle relationships and what they mean, what they are, like the corresponding angles, the same side interior angles, and the alternate interior angles. Excuse the bell in the background. But we're going to be using those, and we'll end up using those to prove that the lines are parallel. In the first section, we kind of assumed lines were parallel, then we know stuff about these corresponding angles and such. But now we're going to kind of flip it around. So our learning targets for this lesson, our first was going to be to develop theorems to show that lines are parallel. So we're going to be developing, so it means we're probably going to be able to write our own theorems and stuff, try to get them without just stating them, and then we're going to develop the theorems, yes. And these are going to show that the lines are parallel. The next learning target will be to determine whether lines are parallel. So once we've found these theorems, we'll go ahead and use them to determine whether lines are parallel or not. Okay, next. So let's start with just number one. So number one, it wants us, before I get you to pause your video, I want to talk about what it's actually saying. So we're stating the converse of each postulate or theorem below, A, B, and C. If you notice, those are the three that we were introduced to in lesson 7-1. So we're going to be trying to find the converse of these. And if you don't remember what the converse is, you can look at this math tip right here. It says the converse of the statement, if P then Q, is if Q then P. So basically what you're doing is you're switching the if and then statements. So if a conditional statement is true, the converse of the statement may or may not be true. So we don't know for sure if it'll be true, but right now all we want to do is state it. So be careful, because it's not as cut and dry as just swapping it in this case. But we'll talk about that in a second. I want you to attempt to do A, B, and C, see what you get. I'm probably going to get you to, after we do part A together, I'll probably get you to stop and revise what you have if you don't have it correctly, okay? Or for the next two. But we'll go ahead and pause your video now and see if you can figure those out. Okay, so as we go over this, as we write the converse of the same side interior angles theorem, I need to first know what the same side interior angles theorem says. It says that if two parallel lines are cut by a transversal, then the same side interior angles are supplementary. So you would think maybe I'm just going to say, if the same side interior angles are supplementary, then two parallel lines are cut by a transversal. But the main thing we want to get away from that second part I just said was that the lines are parallel, because we're proving that these are parallel. So we're not going to have, just think about it this way. You cannot have same side interior angles if the lines aren't cut by a transversal. So we have to keep that lines being cut by a transversal part in the hypothesis, in the if statement. So let's go ahead and look at what I have for the converse of the same side interior angles theorem. I've got if the same side interior angles are supplementary when two lines are cut by a transversal. See, it's a little bit different. We kept that two lines are cut by a transversal in the if statement, okay? It's important because that has to happen to even talk about any of this. So we need to keep that two lines being cut by a transversal in the if statement. So if the same side interior angles are supplementary when two lines are cut by a transversal, then the two lines are parallel. What this means is that if I see two lines and there's a transversal going through them, as such, and then I look at the same side interior angles, and I say I know the measures, say one is 60, oh, excuse me, that's not 60 degrees. Say one is 150, and say one is 30. Okay, if I know those two measures and I see they add up to 180, and I know their same side interior angles, then from there I can say that the two lines that are being cut are parallel. It's a very nice thing. It's a very nice thing we have here. Okay. All right. So what I want you to do now is I want you to go ahead and try part B and C. You've already done it, but I want you to go ahead and see, if you did not get part A right, I want you to take a second and try to revise your part B and C based on the structure of the way I wrote my converse in part A. So go ahead and pause and try that. All right, so hopefully we fixed our mistakes, and let's check and see. So again, we want to see what the alternate interior angles theorem says. If two parallel lines are cut by a transversal, then the alternate interior angles are congruent. Okay? So part B is going to be very similar to part A, except we're going to be dealing with same side interior angles, and they won't be supplementary this time. If the alternate interior angles are congruent when two lines are cut by a transversal, then the two lines are parallel. Okay? So again, I can draw my two lines being cut by a transversal. And if I have this angle being, say, 30 degrees and this one's 30 degrees, if I know those two measures, and I know their alternate interior angles, then I can say that the lines are, in fact, parallel. Last one, for the corresponding angles postulate, that says if two parallel lines are cut by a transversal, then the corresponding angles are congruent. So the converse would be if the corresponding angles are congruent, then when two lines are cut by a transversal, then the two lines are parallel. So if I have corresponding angles, remember they're both on the same side of the transversal, and then one's on the outside, one's on the inside. So this is 150 and this is 150. Then those are corresponding angles and they both have the same measure, so they're congruent, meaning that the lines are now parallel. That tells us that. These three statements are very useful in proving that lines are parallel. So in the next section we'll be proving lines are parallel, and these will be very integral in doing that. Okay, moving on. So we've got Matt still working on the blueprint for the new patio as shown on the next page. It's in your book, it's shown on the next page. I just grabbed that from there, but right here I've gone ahead and put the blueprint for his patio right here. So what we want to do is we're going to be adding information to the blueprint as we work through the lesson. So we're going to be looking at this picture a lot. All right, to ensure that the rows of bricks will be parallel to the walkway, because that's important, that's our whole basis of this thing, Matt extends the string line along the edge of the walkway and labels points X, A, Y. Okay, so that's a line X, Y right there. He also labels points B, C, D, and E, where additional string lines will cross the gas line. So those are going to be pretty much like intersection points where it'll cut this. This is going to be our transversal, that up and down line, and those points that we've labeled there be where new lines that we're going to draw will cut the transversal. Okay. Number 2. Let's go ahead and follow these steps. So what I want you to do before I even go ahead and we'll go over number 2 again, work out number 2 on your own, see if we can get it. You will need a protractor for this one, okay, because you're going to have to measure some angles. So if you don't have one now, go ahead and pause your video and see if you can find a protractor. That'd be great. Okay. All right, let's do number 2 now. So follow these steps. Step A says to use a protractor to measure angle HAX. So angle HAX is right here. All right, angle HAX. So if you get a protractor out, what you're going to do is you're going to stick your protractor, the center of it, on point A, and then the flat side will go along this line right here. So it'll be like a big circle right here. Okay, and if you do that, you read that this line is going to form a 65-degree angle. So that angle, I just put a little blue hump there to signify that's the angle that we're looking at, angle HAX, and angle HAX has a measure of 65 degrees. So hopefully you found that or something very, very close. If you're off by like an angle or two, that is all right. Okay, that's all right. Okay, part B. We're going to use this angle, this measure in a second. So part B says to locate a stake on the left edge of the patio. So on the left, we're over here. Oop, go back. Okay, so locate a stake on the left edge of the patio at point P by drawing BP. And so that the measure of angle HBP is equal to the measure of angle HAX. Okay, so I've gone ahead and done that right there. You see BP, in drawing BP, we now have a new angle called angle HBP, and it wants us, that has to be the same measure as angle HAX, so it's 65 degrees. So what you can do again there, you can put your protractor on point B, and then wherever, find 65 degrees on your protractor, and then mark a point where it intersects this little squiggly line, okay? And once you do that, connect the dots, and we now have a 65-degree angle, okay? Why did we want a 65-degree angle? We'll talk about that in a second. The reason we wanted measure angle HBP to be the same as the measure angle HAX probably has something to do with the type of angles they are, and if two angles are that have the same measure, that we know they're congruent to, so that tells us something as well. All right, locate a stake on the right edge of the patio at point J. So you're going to have to draw in point J. But all we're going to do is extend BP in the opposite direction, meaning it's going to be a straight line all the way through to the other side of the patio. And that's what I've gone ahead and done right here. So we've got two lines that look pretty similar, don't they? You can almost say that they look parallel. I wonder if that's going to be the case. All right, so sorry about that. All right, let's next. Number 3. So this is kind of where I was saying we need to think about what this is saying, and what does it mean that we have those two angles that were congruent? What do we know about the lines? So first thing I want to think about is, let's look at what we have. All right, angle HAX and angle HBP, they're congruent. We know that. We also know that they are a special type of angles, right? They're either alternate interior, corresponding, or same side interior. But which one are they? They are corresponding angles because they're on the same side of our transversal, which is that up and down line, the vertical line, and then they're both on the same side of that transversal, and one is on the inside of the two lines, and one is on the outside. So the measure of angle HAX is congruent to the measure of angle HBP. Okay, we know that. Measure angle HAX and HBP are corresponding angles formed by PJ, and line PJ and line XY being cut by line AB. Very good. So since the corresponding angles are congruent when two lines PJ and XY are cut by transversal AB, we conclude that PJ is parallel to XY by the converse of the corresponding angles postulate. Okay, because remember, the converse of the corresponding angles postulate just says that if the corresponding angles are congruent when two lines are cut by a transversal, so we have two lines, this one, and it's being cut by this transversal, and then we have two corresponding angles also being congruent, so now we can conclude, based on that converse, that the two lines that are being cut are parallel. It's great. I love it. It's a very nice way to show that two lines are parallel. So that's how Matt knows without a doubt that the lines that he is drawing and that are parallel, so that his walkways or his bricks will be parallel. So coming up, we're going to be doing these for C, D, and E, I believe, with the points in there. So, and that's what we have right here. Number 4 through 5, 6, and 7 are all a little bit more drawing stuff in here, okay? And we're going to kind of do similar to what we did in number 3, but we're going to use alternate interior angles, then we'll also use same side interior angles, okay? So go ahead and do all these yourself real quick. I think I really want you to use kind of what we did in number 3 as your guide for doing 4 through 7. It should help you out a little bit, okay? So go ahead and pause the video right now and try to get that yourself. Okay, so number 4. Matt realizes that he is not limited to just using corresponding angles to do these parallel lines. So we're going to use a protractor, again, to draw another parallel string through point C, this time on the blueprint and this time we'll use alternate interior angles. Then we'll mark the angles that we used to draw this new line. So our two lines that we want to be parallel now will be the one that goes through C and then the XY, okay? And we'll use the alternate interior angles formed by those. So I'll go ahead and draw my line. I'm looking at, all right, so first off, I know that I marked this angle BAY, okay, because that's going to be one of my alternate interior angles that I will be using, okay? I marked it in red there if you saw. And then maybe know the measured angle BAY is 65 degrees, and that's because HAX was 65 degrees and they're vertical angles, so they have the same measure. All right, I draw a new line, okay, just like it said to, and we want it to be parallel, and I don't know right now if it's parallel because I don't have any statements tell me that it can be parallel and proving that it's parallel. But it looks parallel, it looks pretty darn parallel to me. So I want to find the alternate interior angle for angle BAY. So I need to be inside these two lines, okay? But then since this one's on this side, the other one has to be on the opposite side. So it looks like this angle right here is going to be our alternate interior angle. And yep, that's what we got right there. So that's angle HCQ, or what we called it, you can call it BCQ as well. BCQ, that's fine. It also could have been called HCQ or anything. Okay, so there were plenty of different names we could have named this, but I called it BCQ. All right, they are congruent because they have the same measure because they're corresponding angle. We want to draw this line such that that is that way. Okay, angle BAY and angle BCQ are alternate interior angles. So if we have the alternate interior angles are congruent when two lines are cut by a transversal, we have two lines and we're being cut by a transversal. So we can say that those two lines are in fact parallel. So QC and XY are parallel by the converse of the alternate interior angles theorem. And basically what I just wrote down in number 4 right there is all the stuff that number 5 is asking you, okay? So just see the answer for item 4 for number 5. Okay, it wasn't very bad. Very similar stuff we did that there. You might be wondering, why didn't I just use HAX to be an alternate interior angle? Well, the reason I didn't, and we can't do that, is because HAX, this one right here, is outside the two lines that we're comparing. So it could not be an alternate interior angle. So that's why I had to move over here and use this angle to show and just use the alternate interior angles there. All right, number 6 we're going to be doing a line through point E this time, and we'll be using same side interior angles. So be careful with this because we've been doing congruent, and we know that same side interior angles aren't congruent, but they're supplementary. So what I went ahead and did, I drew my new line. I drew a line such that these two angles are supplementary. Okay, so I'm looking at HAX and SEA, those two angles. So if they're supplementary, we know that their angles add up to 180. Since I know that measure of angle HAX is 65 degrees, I know the measure of angle CEA has to be 115. I can find this by subtracting 180 minus 65 degrees, and that gives me 115 degrees. So, yeah, okay, so because they're supplementary, we said that, yes, and then angle HAX and angle SEA are same side interior angles. So same side interior angles are supplementary when two lines are being cut by a transversal. Then those two lines are parallel, meaning that line SE is parallel to line XY by the converse of the same side interior angles theorem. Okay. So these examples are kind of cool because they're a little bit different. You know, they're not just going through there and I'm teaching you and we're writing down this statement. This kind of goes through what someone might do in the real world and be able to use these theorems. They might not call it the converse of the same side interior angles theorem, but this is the theory behind it, and it's good stuff. All right, number 7, just the same thing, just see answer for item 6 because we just explained it and I wrote it all in when we did number 6. Okay, moving on. The converses of the same side interior angles theorem, the alternate interior angles theorem, and the corresponding angles postulate are all true, as indicated by the string lines you drew on the blueprint back then in the past slide. So look back at item 1 in this lesson to review the converses of these theorems and postulate. So we know them, we kind of gone over them. I'm not going to go back to that slide, but you can go ahead and look if you need to and pause your video and look at those converses if you need. Number 8. Matt's assistant sets up 2 string lines as shown. Matt finds that the measure of angle 2 is 63 degrees and the measure of angle 5 is 65 degrees. Explain how Matt can tell that the strings are not parallel. So what I want you to do is I want you to think about this, pause your video, and go ahead and write down an explanation for this. And then we'll go over it. Okay, so let's think about what this is saying. So we have one measure of angle 2, that's 63 degrees, so measure of angle 5 is 65 degrees. So think about what type of angles these two form together, or do they? Does this pair of angles any special type of pair? Angle 2 and angle 6 are in fact corresponding angles because they're on the same side of our transversal to the right of it, and then one's on the inside and one's on the outside, and they're also non-adjacent. All right. Angle 2 and angle 6 are not congruent since they have different measures. We like when corresponding angles are congruent because then things work out for us and then we know that the lines are parallel. The converse of the corresponding angles postulate tells us that the strings can only be parallel if the corresponding angles are congruent. Since they're not congruent, we cannot say the lines are parallel. So the strings are not parallel, and that's why we can't say it, because of the converse of the corresponding angles postulate. And the next problem kind of wants us to see if we can fix that somehow. Is there anything that we can do to make them parallel? So that's in our check for understanding. I want you to go ahead and do, I think there's 3 of them in there. Yes. So go ahead and pause your video again and see if we can get those finished real quick. All right, refer back to item 8. How can Matt adjust the strings so they are parallel? So remember we knew that angle 2 was 63 degrees, angle 6 was 65 degrees. So go ahead and move this string down, the bottom string down a little bit. We can make the measure of angle 6 be 63 degrees. So you're going to make it, just move it down, and it's going to drop the measure of that angle 2 degrees. So the measure of angle 2 is now equal to the measure of angle 6, and that means they're congruent, and then thus the strings would be parallel if we did that. That's our answer for number 9. Number 10, what is the inverse of the alternate interior angles theorem? Is the inverse true? How do you know? So what is an inverse? Remember, we've been doing converse today. Inverse is different. Inverse is just when we negate both the hypothesis and conclusion. Meaning if P then Q, the inverse would be if not P then not Q. So all you're doing is taking the negative of each statement in there. So the inverse of the alternate interior angles theorem says that if 2 lines cut by a transversal are not parallel, then the alternate interior angles are not congruent. Is this true though? Yes, it is. And why? This is true because the inverse and the converse of a statement have the same truth value. If you remember when we went over inverse and converse, we talked about their truth values, and in there we said that if the converse is true, then the inverse is true as well. Okay, so or the other way around, either way. So if one is true, then the other has to be true as well. You don't even have to prove it. You don't even have to think about it. If you know the converse is true, you know the inverse is true automatically. But you can think about it too. If 2 lines are cut by a transversal and they're not parallel, okay? If they're not parallel, there's no way that our alternate interior angles are going to be congruent. So that has to be true. So since the converse of the alternate interior angles theorem is true, the inverse is true as well. I kind of just wrote the same statement twice. I'm just realizing that. Oh well. Number 11. Now we're going to complete the proof, and we'll be done for with this lesson. So give me a second. My computer's about to die. Okay, so let's just do this proof. So we've got, we're doing the proof, the converse of the corresponding angles postulate. So the corresponding angles postulate says that if, the converse of it says that if the corresponding angles are congruent when the two lines are cut by a transversal, then we can show that they're parallel. So as a result, our given statement is, we're going to say that we're given that angle 1 is congruent to angle 5. Those two are corresponding angles, and they are, we're going to assume that they're congruent, and we want to prove that that angle, line M is parallel to line N. Okay. So here's what we have. Here's what you see in your book. The first statement we know for sure is going to be that given statement, right? Always the given statement. So angle 1 is congruent to angle 5, and the reason is given. So the number 2, the measure of angle 1 is equal to the measure of angle 5. That's by the definition of congruent angles. We know if two angles have the same measure, then they are congruent. That's what the definition of congruent angles says, and that's what we can go to number 2 because of the statement from number 1. All right, so look at angles 1 and angle 4. They form a linear pair, and we know that linear pairs are supplementary by the linear pair postulate, and that's what statement 3 says. The measure of angle 1 plus the measure of angle 4 is 180 degrees because they're supplementary. So that's by the linear pair postulate. They gave us that. So for the next step, see, what I'm trying to figure out, let's look at what the difference between step 3 and step 4 is, okay? Step 3 has the measure of angle 1 plus 4 is equal to 180, but step 4 has the measure of angle 5 plus the measure of angle 4 is 180. All we did was substitute in 5 for 1 and this from 3 to 4. So if we're substituting, the reason for this would be substitution. Okay? Step 5. Angle 5 and angle 4 are supplementary. I can go from step 4 to step 5 somehow because it's a logic progression right there. If their measures add up to 180, then I know that they are supplementary. And what tells me that? So what tells us that if two angles measures add up to 180, then they are supplementary? That's just the definition of supplementary angles. Okay, 6, last step is easy. It's always the proof statement, so it's just that M is parallel to N. But now that we've shown that those two are supplementary, yes. Right. Now that we've shown that they're supplementary, and angle 4 and angle 5 are actually same side interior angles. We know that if same side interior angles are supplementary, then the two lines are parallel. So we can use the converse of the same side interior angles theorem as our justification for that. And that's it for this lesson, guys. Your homework will be posted on Blackboard, and if you have any questions, feel free to email me at hunter.padden@cpsb.org, or we'll answer questions in our question session. All right, have a great day.